All right, so this is a pretty unstructured lecture today, as I said before. I do have one quick announcement, which is this Thursday at noon in this room, Bobby Johnson will be giving a presentation at the CMS Partners Program Tech Talk. Bobby Johnson is a Caltech alum. He was former #3 at Facebook from 2006 onwards. He was Director of Engineering for most of Facebook's early growth. And he is currently CTO at a company called Interana. And he'll be giving a tech talk on Thursday in this room at noon. So please come to that if you're interested in learning about what he's up to now. Okay, so with regards to, and also there's a recitation tonight. With regards to the lecture today, I didn't really have a plan. If no one asks any questions, we're done. But you know, if people do have questions, I'm happy to go over any parts of primarily HMMs. Although if you have questions on other recent topics, we can sort of go over those as well. So anyone. I don't mind the awkward silence. I get to stay in a row. Yes?
Can you explain generally what dynamic programming is?
Sure. Let me just go to the slide. Okay. So this will be discussed in very, very painful detail tonight if you're going to go to the recitation tonight. Today's Tuesday, right? Yes. But generally speaking, dynamic programming is useful when two conditions are met. First, there's a combinatorial search space, which means brute force search is exponential time. And so you need something that is a little bit smarter than that. And second, that the problem doesn't factorize into independent prediction problems, right? So if you were just to predict, if somehow it was sufficient just to only look at every token and make a prediction of every token independently, and that is somehow the optimal thing to do, without looking at neighborings or windows or anything like that, then you can just make a prediction on every token independently, right? And that's a trivial algorithm. Everything that we've done up to now, right? So dynamic programming is useful in that sweet spot where you want to do something more complicated than making independent predictions. The predictions have dependencies between them, and there are certain structure that allow you that you can exploit to avoid a brute force search. Specifically, the form of structure is called is that you can identify the minimal set of overlapping substructure in the problems. And in the context of sequence prediction, the notion of overlapping substructure lies in the fact that these probability tables, that's probability models. Let's see here. Yeah, we can just stick with this one. Right, the probability models. You know, what makes the best possible prediction is finding the y that maximizes something like this, right? And so this is where you have the dependency between the predictions, right? If this term didn't exist, the problem would factorize into capital M separate naive Bayes prediction tasks, right? That you can just predict independently. Because of this pairwise adjacency, somehow the best sequence of y's that maximizes this probability, you have to take into consideration all the dependencies. But there's only pairwise dependencies here, right? The relationship between everything that you've predicted up until the current token and the next token, everything just is summarized by this single probability table. And that is the minimal set of overlapping substructure between the different subproblems in the prediction tasks. And by identifying that, you can design a dynamic programming algorithm that can exploit that structure that does not lead to a brute force exponential time algorithm. So that's the high-level intuition of when dynamic programming is useful. You can do dynamic programming in two-dimensional problems. This is just a one-dimensional problem. You can do two-dimensional as well in certain cases. Other people refer to this as a form of what's called memoization, if you've ever heard that term in your algorithms or data structures class. Memoization is basically a term used to design some sort of data structure or a storage scheme where you basically only need to store a few numbers to capture all the sufficient statistics of what were the optimal predictions up until this point in time. You've memoized the solution up until the current point in time. And then you just look at that table of currently memoized solutions to move forward. And so these terms are in some sense, highly interchangeable, these concepts. They're all referring to more or less the same thing. Yes?
Is it true that every dynamical programming solution can be reformulated as recursive? Are these two things equivalent?
I'm not an algorithms person. I didn't even get to any of my algorithms class in undergrad. But don't let that stop you. I think the answer is yes, because dynamic programming in some sense is very general, right? If the optimal overlapping substructure is the entire problem, then dynamic programming is still in theory applicable, it just runs in exponential time, right? So here, dynamic programming runs in time that is quadratic in the number of part-of-speech tags because of this table right here, right? If somehow we had to model long chains of dependencies, right? In particular, the entire sequence of length m, then this algorithm, even it would run in time that's exponential enough. Right here, it's exponential in the size of the dependency here. Here, the exponent is 2, right? And so dynamic programming is in principle, you can apply dynamic programming principle to any problem. This may not be useful or give you any gains. You can apply recursive programming in principle to almost, I think, any problem. If you've taken, do you guys do like CPS style programming, like continuation passing style? You guys, does that ring a bell? Well, anyways, so I think the answer is yes. Yeah, because these are very general concepts. The question really is, what does it buy you? You can always tell if the class this year has started on the homework yet or not by how many questions are asked during this lecture. Yes?
So there's a numerical example of the interpretability algorithm that you lectured last time. Like, can you go through again, like, which part of the data can be thrown away during the process and what should be like always kept for backward pointer?
I'll use this one because it's more generic, even though it doesn't have specific numbers on it. First, just a reminder of the notation. Capital Y hat, superscript K of, in this case, verb. So there are 3 part-of-speech tags that we're going to consider in this example: verb, noun, and determiner. And so this notation denotes the best length K prefix sequence that ends in the tag verb. Okay? And so this is just by definition what it is, right? You take an argmax over everything before the length K. You compute the probability of this set of free variables, append verb to it, and then you want the thing that maximizes this, and then you append verb to this y. Right? This is just definition. So this is the best, and this one refers to the best length K prefix subsequence that ends in the part-of-speech tag noun, right? And so the claim is that when you compute if you've pre-computed all of these, right, you've memoized the solution up to this point, the best length K plus 1 prefix subsequence that ends in verb can be computed using these previously computed solutions without going over all possible length K prefix subsequences to find the best one. So that's the claim, right? So it suffices at every iteration in dynamic programming to only keep track of these solutions, right? And so pictorially what that means is we have a base case and an inductive case, right? The base case is when the K equals 1, and And so computing these length 1 prefix subsequences that end in a certain part of speech tag Z is trivial. It's just that part of speech tag, right? It's a singleton sequence. And so we store that into these prefix solutions. We also store, as for bookkeeping, the probability of this, this partial probability of this length K prefix subsequence, right? The inductive step is where it gets interesting, right? In the inductive step, and here I'm showing it for K equals 2, right? We want to compute the best length K prefix subsequences for K equals 2 for the 3 part of speech tags in our graphical model, in our hidden Markov model. And so we can start with the first guy, right? And so the only 3 possibilities are going from the sequence stored in this guy and appending verb to it, going to the sequence stored in this guy and appending verb to it, or going to the sequence in this guy and appending verb to it. Okay? And then we compute the partial probability that corresponds to that sequence, and then we pick the one that maximizes, that has the maximal probability. Furthermore, the partial probability of the prefix sequence, of the prefix part, is already stored right here, right? And so the only thing we need to multiply to this number are these 2 numbers, right? And so, and the reason why this whole thing works is because the only thing that depends on the past predictions is this transition probability table right here. This is the only thing that connects the current thing we're trying to compute to the previous solutions that we've already computed. And notice that this thing only depends, oops. And notice that this thing, for K equals 2, this thing only depends on the final prediction at K equals 1, right? It doesn't depend on anything before that. And this makes more sense if you look at K equals 3, right? At K equals 3, the thing that connects the quantity you're trying to compute here, the best length 3 prefix subsequence that ends in verb, the only thing that connects what you want to compute here to all the solutions you've computed previously is this probability table right here, which only depends on y2. It does not depend on y1. Right? That's why. I don't know if I answered your question or if there's something other point.
So I guess it's more clear in the numerical example that you throw away several. You compute, like for each step you compute some probability and then you trace out something.
Right. So here, so you're talking about this example, right? Yeah. So the flow diagram is a flow diagram of the probabilistic state transitions y. And then this is so that's the A matrix, and this is the O matrix that corresponds to the observation likelihoods given that you're in a specific Y. This example only has 2 part of speech tags, noun and verb, and a dictionary size 2 fish and sleep. Okay? And so the first token, the first X is fish, right? And so we compute the probability of going from the start state to verb, or from the start state to noun, right? And then from that, we compute the observation likelihood of, given that we're in verb, what's the probability of observing fish? Given that we're in noun, what's the probability of observing fish? And so this is the probability. So this is the base case, right? This is the base case. And we store, we store the probabilities. And the inductive step, happens when we look at the best length 2 prefix subsequences that end in verb or noun, and we consider, and the second word is sleep, right? And so if fish was a verb, how would that impact computing these 2? And if fish was a noun, how would that impact computing these 2? And so point 1 here refers to the let's see. Point 1 here refers to this number right here, right? That was pre-computed. This number was pre-computed. And then this number corresponds to the transition probability of verb to verb. And this number corresponds to this 0.5, right? And so here, this point 1 is pre-computed, right? This point 2 corresponds to the probability of going from verb to noun, right? And then this point 2 is from this probability table, right? And then we also consider what would happen if we went from if the best length k minus 1 prefix subsequence, here k equals 2, so k minus 1 equals 1. The best length 1 prefix ends in noun rather than verb, and so we take this number, 0.64, we've already pre-computed this number, and we multiply the transition probabilities. So the 0.8 comes from going from noun to verb, and the 0.5 is from the lookup of this probability table, and this 0.1 is the probability of going from noun to noun, and the 0.2 is from this observation table. And then we just take the max over these two, right? When you compute the best length 2 prefix subsequence, you only need to look at the best length 1 prefix subsequence, consider appending a verb to both of them, computing the two probabilities and taking the maximizer, which is this guy, and for noun, it's this guy, right? And so now we've committed, at this point, we've committed to the best length 2 prefix subsequences that ends in verb and ends in noun. We've committed to them. We've memoized the solution up to this point. And you could actually read off the best length 2 prefix subsequence by, if you represent it this way, which you can with a linked list, so a type of data structure, you can actually just read off the solution. And then when you go to 3, length 3, oh sorry, length 3, it has to be the end token in this example. And then for the final solution, you just take the best, the subsequence with the best overall probability. Yes.
So in supervised learning, we just do counting for hidden Markov models. But in unsupervised learning, you mentioned these marginal terms. I think you say that we use the alpha and beta terms to calculate these marginals. And I'm not exactly sure what kind of math we have to do to do that. So I guess can you go over kind of that final part of using those alpha and beta?
I'm not sure. It might make sense.
Might be more in your notes.
Let's do that. All right. Refresh the memory of these notes real quick. So, right, so can everyone see this? Can you see this in the back? Is that okay? Okay. No? Someone say no? Okay. Let me just zoom in. You don't need to read the text. Is that better? Okay. Okay. So, right, so in supervised learning, you're given examples, y comma x. Here x, I just use the entire sequence, but it only really looks at one token at a time for this example. You're given a supervised sequence where you know for a fact it's a certain part of speech tag, right? Which I denote by free variable a. And so you know for a fact that it's a 1 for a specific value of a and 0 otherwise. Right, that's counting. In unsupervised learning, we're going to use an EM algorithm where we actually just estimate the marginal probability that it's an A for any free variable part of speech tag A. Right? We're going to do that for ignore for now what alpha and beta are. But if we pre-computed these alpha beta vectors, we can just do that using this formula. And this will give us a soft count, right? And then it reduces the standard supervised learning. So now the question is, what are the alphas and betas, right? And so, the definition of alpha is something that is proportional to basically the probability of a prefix sequence, the partial probability up to some prefix subsequence, right? Which is so alpha sub notation is alpha sub a of j, where j is the where you are in the sequence, and a is the free variable denoting the part of speech tag. Well, I guess this lecture notes was agnostic to the application. So A is just the identity index over a latent state or hidden state. And so this basically alpha has this definition where you sum over all possible length j minus 1 subsequences, right? And then you sum up this total probability, right? Where the j token equals a, right? And beta does it from reverse, where beta looks at all the suffix subsequences, right? And computes its partial probability over the suffix subsequences, right? And then you could easily, well not easily, but it's straightforward to convince yourself that this is the solution by just using standard laws of marginal probabilities. And so what kind of math? So what kind of math does one need to do to actually compute these things? Well, let's see here. Well, ultimately, you have to use a form of dynamic. Yes. Yeah, sure, of course.
Why do you have a joint probability for alpha, but for beta you have a conditional probability?
It's joint here.
Right, I mean, for the first.
Oh, right. It's just a. I see. It's to get the math to work out. You don't want to double count any term in the factorization. So here we condition on yj equals b. Here we compute, we incorporate yj equals a as part of the probability. It's so you don't double count any term. And when you combine alpha and beta vectors, you don't double count any term in the whole multiplicative factorization. Okay. And I guess I should just say that, if you move this guy over there, I mean, it doesn't really, well, it's going to be mathematically more awkward if you move this guy up there, but it'll also work out. You could also rederive some notion of this formula. This guy has to be in one of those two places. So ultimately, there's a form, you use a form of memoization or dynamic programming as well to compute these alpha and beta vectors. This is the update rule, right? Where you can write them recursively as a function of the previous alphas and betas that you've computed, right? And so, I guess one question that arises is numerical instability, right? So when you actually implement this in practice, these probabilities become very small very, very quickly. They decay geometrically with the length of the sequence. And so if it was really as simple as implementing these two, this is really straightforward, right? Just a couple of matrix operations of probability tables, right? And so you have to deal with numerical instability, which I guess I wasn't able to cover in lecture on last Thursday. And so the way you deal with numerical instability is you observe that the only thing that matters, right, is that you maintain proportionality. The only thing that matters is that you maintain proportionality because you normalize. You normalize by the same stuff, right? And so if you multiply all the alphas and betas by a factor of 1,000,000, you get the exact same answers when you compute the ratios, right? So the only thing that matters is that you maintain proportionality. And thus, you have this type of update rule, right? For some choice of C alpha and C beta, such that overflow does not happen. And so this is a different C at each point in the tokenization. So for example, if I were to compute this guy, right, the numerator is multiplied, compared to the original formula, the numerator is multiplied by C sub alpha j and C sub beta j. The denominator, same thing, so it cancels out. If you look at this guy, the numerator is multiplied by C sub alpha j plus 1, C sub beta j, C sub beta j plus 1. The denominator is multiplied by the exact same set of terms, so it cancels out. And so the trick then is how do we, when we compute these solutions iteratively, we keep renormalizing at every iteration of the sequence, such that you preserve proportionality and you avoid numerical instability. So usually, in practice, you choose the C as the sum of all the alphas, right? So locally the alphas sum to 1, and locally the betas sum to 1. But it doesn't really matter. Was that your? Did it answer your question? Okay. I feel this urge to cancel class right now as he walked in. It's like a joke. Yes.
And so when I ran unsupervised data model every time, I get very different results.
That's right. That's right. EM algorithm will converge to a local output.
Okay.
Based dependent. If you use the same initialization, you should get the same answer every time.
Yeah, but it's random.
That's right. Yeah, it'll converge to a local output. In particular, I can permute all the hidden states. You get the exact same solution. Yes.
So in the last part, when you have to like interpret the word clouds of the clusters for the Constitution, how interpretable do you expect the word clouds to be?
They're not going to be the most interpretable, but you should be able to make some inferences. One of the challenges with these interpretability things, especially for text, is that most of the latent factors will contain a lot of the common words, like the, and, etc. And so interpretation really involves sort of going beyond that, right? If like the most common words in every topic or hidden state was the, that's not very useful. And so what people often do, I mean, there's a number of different ways to get around this. One thing that people often do is they look at, what are the words in this hidden state, in this state, that are very rare in the other states. So you do some sort of ratio, or you do something that looks like something, or difference, or something like that. So if the is really popular in all the topics, or all the hidden states, then it's not very interesting. But if the word, what is the text you guys are modeling?
Constitution.
Constitution. If the word like, Bill of Rights does that include the Bill of Rights?
Don't know.
Okay, whatever. Okay. If the word it contains the word independence, right? The other hidden states don't contain the word independence, then that's interesting. And how do you measure? And I guess all of them will contain some small probability mass on the word independence, but there's one that has really high mass on that, and the other one's much lower. That tells you something. And so there are various formulae that people use to quantify what that means, and I don't think anyone really agrees. But if you look at around on Wikipedia or ways people compute these like surprise factors, what is the where the two distributions sort of are most different, then you can sort of find a way to sort of visualize that part out. Yes.
How do I initialize alpha 0 without the starting states?
If you don't have any prior information about the starting states, you can just initialize to be uniform.
Sir?
Uniform.
Oh, okay.
Yeah. If you do have information, then you can. I mean, it depends on the model, but it's yeah. That specific detail is best probably left to ask the TAs, because they may have a specific model in mind. Yes.
These, the second marginal term, number 13, those two middle terms, those correspond to the O and A matrices.
This corresponds to the A matrix, this
Yeah,
corresponds to the O
yeah,
matrix.
O and A matrices.
That's right.
So those are the O and A matrices of like the last iteration if we're going to be running this in kind of an iterative form.
Right, so like if you were just
Because
marginalizing
we're
one
using
of
these marginals to calculate new O and A matrices, correct?
That's right.
Okay, so then
That's right.
those are the values in the O and A matrices.
That's right.
Like, I guess we're running this in an iterative
That's
fashion.
right. Just like in K-means clustering, you use the cluster centers to then in one step
Yeah,
you do
yeah.
cluster centers, one whole step, right?
Because I just kind of
Yeah.
saw like this.
That's right, yep. And K-means also converges to a local optimum. Yes.
So this is more of a conceptual question, but for, I guess I'm wondering, why do we decide to maximize, why do we decide to take the maximum likelihood rather than some other like median likelihood, average likelihood? Because those might, generate a model which has, better representation of data.
So, right, let's go back to the slides. Right, so why do we pick the parameters of the model that maximizes probability? Why don't we do something like average likelihood, right? So in a sense, we are average. There's two notions of averaging. One is averaging over the training set, and one is averaging over multiple possible parameterizations of our model. We are averaging over the training set, right? Because we're looking at, if you take the log, it's an average negative log loss, or an average negative log probability, or the average log loss over all the training samples. So when we're looking at the training set, we are actually taking an average, effectively, right? As for whether or not we're not averaging over multiple different possibilities of our model, well, one question is, well, how does one compute this probability if there are multiple possible parameters? Is it an average? So it would be like a sum over multiple different parameters of our model, and the average of the set of probabilities. But then which one of those would you use to make predictions? Would you use their average? Now, actually, people do that. It's called that's called Bayesian. That's called hierarchical Bayesian modeling. People actually do that, where they don't want to commit to a single parameterization. They want to commit to a distribution of our parameterizations, and then they maximize the average of this within that distribution. Or actually, since each data point is independent, the sum can go inside the probability. The sum can go inside this product. One second. Yeah, because they're independent, yeah. So it doesn't matter, I guess the order is, yeah. Well, people do that, right? But then the question is, okay, what do you use this collection of models for, right? Some people use it to reason about uncertainty estimates, right? So if you actually care about how certain you are of your probability estimates, or your model estimates, how spread, how much variability there is in this distribution you've estimated gives you a notion of confidence. They're typically less useful if you want to make a single prediction, right? Because they spread things out too much. But if you want confidence intervals and stuff like that, then it's typically more useful. And in fact, let's see here. So here's an example of a hierarchical model, right? Where this is a very different model, but it's just an example of a hierarchical model where you're sampling multiple layers of parameters, and how you sample parameterizations of one part of your model is actually defined by distribution over parameters you sample from. Ultimately, they have these alpha and beta parameters that are deterministic, and these are also trained on the data set. And then you have these layers of sampling parameters of nested models. Yep, so I think I'm going to cut lecture here since it seems like people are winding down on questions. If anyone does have any further questions that pop up, I will use the rest of lecture time as office hours. So I'll be in my office until 4 o'clock.